All right. Thank you, everyone. We are going to talk about machine learning on CPUs. So let me introduce a little bit about what we do at ThirdAI. And again, we build software libraries to train and fine-tune billion parameters, neural networks, large language model, or retrieval augmented generation, all on CPUs. And again, I will restate, we train and fine-tune, because whenever we think about AI on CPUs, the common perception is this is talking about inference. We are not talking about inference. We are talking about training, retraining, fine-tuning, and reinforcement learning. We can do that on CPU. To get started, I'll go over a small video that we created.
Don't wait. Buy your graphics card today.
The next GPU shortage is coming, and honestly, I'd recommend buying a GPU sooner rather than later.
The shortage of NVIDIA GPUs, which is causing havoc on the AI markets.
Companies are buying way more GPUs than before thanks to the new AI boom.
There's still industry talk of yet another GPU shortage.
Even if TSMC started working on it immediately, you would not get a chip out for 3 more months.
We are facing a GPU shortage because everyone wants generative AI. And generative AI can only train and fine-tune on GPUs. At least, it used to. Introducing Bolt 2.5b, the world's first generative large language model entirely pre-trained on CPUs. Let's see how it compares with a 1.5 billion parameter GPT-2 XL. Under the hood is our Bolt deep learning engine, which uses dynamic sparsity to selectively train only the neurons that are relevant to each training sample. This allowed us to train this 2.5 billion parameter model on 40 billion tokens with 10 Sapphire Rapids machines in just 20 days. With this level of efficiency, fine-tuning is more accessible than ever before. After just 1 hour of fine-tuning on the works of Shakespeare using a Haswell machine, we were able to turn this into this. There was no pruning, quantization, or low-rank approximation involved. So think about the things you can do with spare compute in your data center. Think about what individuals can build with their own laptops or desktop computers. Think about using cheaper alternatives to GPU instances for generative AI workloads.
So as you can see, we are talking about training AI on CPU, and for a comparison, we have trained the world's first generative large language model entirely on CPUs. So this was trained on 10 Sapphire Rapids cluster. Obviously, the distribution was done with an interconnect and on a ray framework. It took about 20 days. It has consumed 20 billion tokens so far, and its capability is at par with GPT-2. So why CPUs? I mean, again, well, we all know about, we are all talking about saving, GPUs and the GPU shortage. Well, another way to save GPUs is to start using more of your CPUs, right? And that is what we are trying to do. So CPUs are readily available. They, if you are doing a better AI on CPUs, it serves much better latency because you don't have to transfer your data from CPU to GPU and back. There is data residency problem. I'll talk a little bit more about it. Cost is definitely a factor. Even if we believe the cost is not going to be a factor in the future, data movement is going to be a future. And we are building an AI ecosystem which is about ownership, as in you are encouraged to fine-tune daily, right? That is kind of an AI ecosystem we want to build. So why this is possible, why now, and other things. So this is a paper that we presented in ICML 2023 this year. It was taking all the models that was released by Facebook. So starting from an OPT 350 million all the way to OPT 175 billion. What we can show is when you run this model feed forward, 99.9 or more than 99% of computations are actually 0 times a number. And so when you do forward pass, you're doing a lot of 0 times a number. When you do backward pass, most of the computations or the gradients are still 0. So essentially, we are wasting a lot of our floating point operations, lot of our computations and energy in calculating these zeros, and probably literally burning billions of dollars in computing those zeros. So at ThirdAI, we have found a way to not compute these zeros. So essentially, this is I'm also a professor, and this is more than 10 years of research that I have been doing. There are dozens of research papers where we showed that there is, and what we call it dynamic sparse stack, there is a scientifically proven way to train deep learning more efficiently. So just a high level overview of this deep learning network here. So imagine that this is a billion parameter neural network, right? So when we do a forward pass, we do billion operation, we get a prediction. Then there is an error, we do billion operation, we get updates, and then we do a billion of updates. At this point of time, we'll say, look, there are 3 billion floating point operation, we definitely need specialized hardwares, and you would be right. But if you go and look into it, you will find that you do 3 billion floating point operation to only update few thousand parameters. Now the puzzle is obviously you cannot throw away parameters. Like if you think about static sparsity, right? Sparsity is now a very overloaded word. So in static sparsity, you may think about, can I throw away parameters? The answer would be no, because every pattern will pick a very different set of 1,000 parameters. And in fact, if you throw away the parameter, that takes away L from that large language model, right? I mean, your model will start becoming small. So essentially, the puzzle here is, how can we figure out the relevant parameters given a pattern, and the pattern is allowed to change dynamically because we don't know what the input is. But well, we have seen that problem before. It's like information retrieval, right? When you do Google search, when you type Ray Summit on Google search, how does Google search knows where to will take you and not like compare with billions of web pages on the planet? That is precisely a technology that we have made to work. So basically, in our Bolt infrastructure, which is our dynamically sparse software stack, when you show a pattern, a very sparse set of parameters are queried from this large neural network, and only those parameters are used for forward propagation, back propagation, and update. So essentially, instead of doing 3 billion operation to do 1,000 updates, we can get away with, let's say, 40 or 50,000 operations. And this allows us to utilize massive scale deep learning training even on CPU without losing accuracies. Just to argue like why we need this now, let's present a case study of why we believe that current software stack is actually fundamentally hard for a lot of our production tasks. So I'm just showing you a retrieval augmented generation framework, right, in which you're taking a Gen AI model, and because the Gen AI model has a short context window, what you do is you do a semantic retrieval. So let's say if you want to ask a question, does my organization provides any retirement benefit? You want to retrieve everything that your organization has which is relevant to answering this question. Then you give it to the Gen AI model and hope the Gen AI model will generate an answer. Now to be able to do this retrieval, people are using embedding models which are now going to work on GPUs, and then there is a whole ecosystem on VectorDB which is likely working on CPUs. Now if you look at this infrastructure and ask a question, look, is this really going in production? Is this really going to scale? So here are some of the challenges. First of all, as you can see, there are two data movements because all your text needs to go to GPU to generate embeddings, and all your text needs to be in VectorDB to be stored and retrieved. So you have created at least 2 copies of your text around, and data movement is not easy. I mean, even if I know GPU cost may go down in the future, data movement will still create that friction. There is another issue here with the embedding models. The current assumption is look at the text that is about like what, 512 characters or something for a chunk. Usually they recommend 256 or 250 characters for a chunk. That's like what, 500 bytes. And if you use OpenAI's ADA embedding model, you are generating 1500 numbers. That's about 6,000 bytes. So you're blowing up your data about more than 10x and then moving it around. The other issue is, let's say in this system, you don't like the retrieval. The reality of everything in production is there is no static AI that will make everybody happy. As you scale, you will not like the results. Who will you blame? Will you blame it to a VectorDB, or will you go and blame it to an embedding model? And if you fine tune an embedding model or refine it, you go and rebuild your VectorDB. And enterprises would want to do it again and again and often. I mean, I think we are not asking hard questions here is why is this friction coming? And we believe that part of this friction is because of this heterogeneity of the hardware. You need a different software stack to understand GPU, a different software stack to understand a CPU, and that is why you are pushing these blocks and puzzles around there, and the software stack is becoming complicated. Again, the question is, let's look at what happens in a VectorDB, right? So what happens is you get an embedding, then embedding goes into a data structure, some form of pointers, key, or memory address that does the retrieval. The question is why a very disconnected process to do that, right? If we could do something like, if it is assumed, the reason why we are doing this is because it is assumed that, look, it's prohibitive to build Gen AI models, so all we can do is to reuse it. Nobody wants to build Gen AI model because it is assumed to be prohibitive. And we are okay with complicating the software stack because right now there is GPU shortage and nobody can build this. But let's say if you could build Gen AI models at ease, then you would ask the question, why go with this complicated stack? Why not just have a Gen AI model that take a text and predict these keys and pointers, and I don't have to go and store the embeddings and do away with like all those memory things, right? I mean, I can avoid data movement. I can do fine-tuning, retraining if I can do this, direct prediction, which is called learning to index in the framework. So this is what we offer. Because we are able to do this whole entire ecosystem on CPU, we offer a database which we call NeuralDB, where you can insert text. I mean, it is like a retrieval augmented generation ecosystem where you can insert text. The text you can fine-tune at will. There is no data movement. Data residency is a problem that we solve. And the system is production ready since inception. We can run it at about 2 millisecond latencies, right? That is the kind of thing that we can achieve. Here is a blog that was written by Wayfair about how they are using ThirdAI in their ecosystem to reduce the latency of their retrieval systems. Again, what is the effect of being able to pre-train your own Gen AI? I think we have already seen that in the keynote earlier yesterday, that if you pre-train even simpler or inferior models, if you pre-train fine-tune, it gets better than most of the sophisticated model. So here is an experiment that what we are showing you is a retrieval augmented generation. We are comparing it with some of the popular models like T5, OpenAI, ADA, and Instructor Large. And what we are doing is we are not even pre-training any ThirdAI model. We just take the ThirdAI model and only pre-train it on the text that was inserted. So you see, there is a difference here. Like, we talk a lot about pre-training, fine-tuning, but you can as well pre-train on the text that you are inserting. It's a domain-specialized pre-training, right? What is pre-training? Next word prediction or some self-supervised learning on a raw text. You can as well do it on the text that you are inserting. What if we just do that? What we realize is you don't need any pre-trained model. You can beat the accuracies of some of the popular foundational models that has been pre-trained for months over like a very expensive infrastructure out of the box. And the reason why you could do it is because you're doing a very domain specialized thing. Here is a demo of a tool that we built, and again it runs on Windows, and like it's a 250 MB app. It can run anywhere, and it is actually doing this retrieval augmented generation on a desktop.
Today, we'll take a look at using Pocket LLM powered by ThirdAI's NeuralDB as a generative AI knowledge base. As a case study, we'll load a NeuralDB that was trained on a university's knowledge base. If we click on this button, we can see that we've inserted hundreds of documents, too many to go through one by one. So we'll use this tool to answer, who can reject a timesheet? Or how to onboard a student? These answers are generated using only information from our documents, since it's important that our knowledge base presents organization-specific information. Because of this, Pocket LLM also displays the specific parts of your documents that are relevant to the question right under the generated answer, so you can go ahead and read the original documents too. Now, no AI is perfect, and sometimes it fails to understand, say, how to motivate a faculty member to stay. In this case, it does not hallucinate, and instead tells you that it doesn't know the answer. It's a difficult question after all. However, if you are a knowledge base administrator and you've heard of faculty retention funds, you can give a hint to the model by clicking this button and associating the query with faculty retention funds. Now, if you ask again, faculty retention fund comes second, but that's still not good enough. We want the model to be precise. So let's give it more feedback and ask again one more time. This time the model gets it right. This is a model that listens to you. But what if the answer is not in this knowledge base at all? Maybe it's in a new document. With NeuralDB, you don't have to build a completely new model just to add new information. All you have to do is click this button and add your new documents. And just like that, your model can now generate answers using those resources too. When you're done making changes to the model, you can save it to your computer. In fact, you may remember that we also loaded this model from a local file, and since NeuralDB runs completely offline on your local machine, Your documents and queries stay with you, as they should.
So in this demo, what you're seeing is a backend API NeuralDB in action in a UI-based demo. There, we uploaded more than thousands of PDF. It was trained on a Sapphire Rapids or a desktop box in about 20 minutes. Then you go and query it. What is interesting here is if you don't like the retrieval, you can fix it on fly. You can either teach it, you can do reinforcement learning, and the model updates on the fly. This is kind of a system which we believe over a period of time it will get better. So our vision for this Gen AI is the entire ecosystem where you are utilizing all your data center CPUs to pre-train a large model, like a Gen AI model or an embedding model. Then you load this model on a local device, all under the ThirdAI stack. Then you can play with the model. If you don't like, you teach it. So essentially, when you deploy this model, maybe the model is 70% good, or the application is only satisfying your need by 70, 80%. As you grow, the model grows with you, because as you use it, you give feedbacks, the model grows better and become useful. We believe this is a much better picture of how Gen AI, how enterprises would want to take Gen AI in their ecosystem and then deploy it in production. So that is basically what the kind of stuff we do. Now comes to the technical aspect of things, right? I mean, how do we scale up sparse training on CPUs? So again, like as mentioned before, we are talking about training billions of parameter models on hopefully terabytes of text. So first few things about training on CPUs, which people are not usually used to. CPUs completely eliminate, more or less, the need for model parallel training, right? I mean, you can assemble a 6 terabyte CPU that I was trying to do even in 2018. That can, even at that time, would fit 7 GPTs in one machine. So we don't have to worry about model parallel training, because model will always fit your node. Now the question is, we only need data parallel training, and we need data parallel training because you have to ingest data at a very fast rate, right? There is a lot of data. And so there are two bottlenecks here. Obviously, one is the communication, and the other is data parallel training. You need to be able to do like ingest data in parallel and aggregate the models. Aggregation of the models means you need communication. The good news here is if you're doing dynamic sparse training, like I mentioned before, most of the gradients could be sparse and easily compressible. So we have that in our routine. The other interesting part, which people have not thought about much, is if you are doing a sparse training, you can increase your batch size significantly. Right? So if every parameter is not affected by all the data set in the batch, right? So imagine if I have a billion parameter and I am running it at 1% sparse. That means 99% of the data is not touching every parameter. That means you can increase your batch size by 100x without affecting the performance. In fact, you will get better performance, and larger batch size is great for data parallel training. So we have all the grounds to make this successful. But what we lack was a data parallel framework which is fault tolerant, performant, auto scaling, and push button. And this is where we use Ray. In fact, it was recommended to us by some of our VMware partners, where they told us to start thinking about Ray. We were using, before MPI, and other alternatives. But we realized that somebody has already solved this problem. So this is basically comes in why ThirdAI and Ray. So we adopted Ray core for data parallel training after evaluating alternatives. The key features that we were using, that was back when we started this in 2022, we were using actor model, auto scaling, and glue integration. We were relying on that a lot. And we were actually surprised by the rapid development of this data parallel system. Then we shifted to Ray Trainer in 2023 because we wanted to take more simplified, create more simplified developer experience, and also there were enhanced fault tolerance and broader integration capabilities that we could take care of. So how ThirdAI uses Ray, right? Well, we have created what we call Bolt Trainer, which is where our distributed data parallel training happens, and it is built on Ray's data parallel trainer. It's similar to Ray's Stars trainer. The experience is quite simplified. I'll show you a snapshot of a code. We also realized that the memory usage were reduced by 2x, and there were options to use more economical CPU instances. Here is actually a code of how you can even, like, this is the code where we use multiple CPUs to train a GPT kind of a generative model. All you have to do is to initialize this bold trainer, and in fact, if you can still visualize, there is a scaling config, which is a typical ray scaling config, and you need like a train loop per worker. And if you write it with ThirdAI and this ray integration, this is the kind of code, less than a page of a code, where you can actually run a job on as many CPUs as you want. This is how easy it is. Again, talking about some experimental evaluation. So we evaluated this on Criteo terabyte benchmark, which is like one of the popular click-through prediction benchmark. It is the largest public data set that is available for experimentation. It has about a terabytes of data for click-through data, and the task is obviously click prediction or not. Here what we are showing is we took a million-sized model, and again with different compression. So as I mentioned about that, because of our training being sparse, we can compress the gradients and communication time. So these are like 50 million model, 25 million model, 37.5 million model. What you are looking on the x-axis is the number of nodes. There is 12 nodes, 24 nodes, 48 nodes. So these are nodes of CPUs interconnected with Mellanox, 100 gigs, 10 gigs, or around that. I think this experiment was done with 10 gigs. What we see here is this is the time, and as you see, the time increases kind of linearly with the model size, which is expected, but it also kind of goes down in almost a linear fashion as you start increasing the number of nodes. So here is the same benchmark, but now on a billion parameter model. So previously there was a multiple million parameter model because we wanted to test how the model behaves as you increase the number of parameters. Now we took a billion parameter model. We see same effect, right? I mean, we have 12 nodes, 24 nodes, and 48 nodes. And this is basically allowing us to take this model and train it, distribute it, all using Ray framework. And all you have to do is to write a page of Python code, initialize a Ray cluster, put ThirdAI on all of it, and get going. Again, there is a whole bunch of details that we have written down on a blog with Anyscale. So please read this blog about ThirdAI training. And this is where I would like to end with, and we have time for questions. I would say that we could utilize all your data center capabilities to train AI, generative AI, and we'll be happy to showcase you how we can do it. Thank you very much. Yep.
In the example that you showed at the beginning, how many CPUs were you using to train, the language model?
So we were using 10 Sapphire Rapids. So this is like the latest generation Intel Sapphire Rapids with like about 100, 200 cores each machine. It's a duo socket. So it's 56 core each socket. So 10 duo socket Sapphire Rapids with 100 gigs Mellanox connected, and then it was initialized on Ray core.
So you show this with the Bolt AI model. Does dynamic sparsity work with any model? Let's say they've developed a model in my lab. Can I use the underlying infrastructure to get the same benefits?
That's a great question. So generally the way so we have a very different approach of making the models work, right? So right now, if there is a foundation model, we can distill it in our framework. So our framework basically initializes the model and trains it. The reason why we get all the benefits, and again, like inference with this model and fine tuning is very fast because these models are made for CPUs. So all we can do is if let's say you have a target model in mind, we can distill it to create an equivalent if that is what we have to do. But essentially, if you think about it, any foundation model is pre-trained on some data set. We can as well pre-train on the same. See, I mean, again, like this is also like a change of perception that we want to happen. Is right now the world is believing, look, fine-tuning maybe it's okayish, inference is easy, fine-tuning is okayish, and pre-training is hard. But what if you can pre-train at will, right? Because what I'm talking about is 10 Sapphire Rapids or your data center cluster, you're training a job overnight and that it's done, it's pre-trained. So if pre-training is easy, you would be doing it more and more often, more and more targeted pre-training, more and more targeted fine-tuning. And we believe that that can happen if we start to leverage all the cores of CPUs. Because right now with GPU shortage, the amount of GPU compute and the cost that is needed to build these models, it becomes like, okay, if somebody has done it, let's not burn the same amount of money to get something that is available. Or even if it's remotely available, we'll still reuse it. But why reuse it when you can build it essentially in no cost? Then this is what our stuff is.
Yeah, so in the last page on the experimental evaluation, I saw the number of nodes doubled, but the training time only improved a little bit.
Yeah,
would that be?
So this is obviously, so this was on an interconnect, and this was a billion parameter model. Okay. So billion parameter model, when you do the communication, it is communication bound. The thing is, even if you go from 24 to 48, we were actually hoping that maybe it will not go down. See, this is not like a large language model kind of a workload, but this is like a terabyte workload with a billion parameter model. So the communication is still a barrier. But even when we double the node size, we still get down on the training time, which was interesting.
All right, if there's no more questions, let's thank our speaker again.
Thank you.